Hi everybody, welcome back. So today we're going to be covering chapter 12, and we're only going to be covering section 12.1 for this particular chapter. Now, chapter 12 deals with the analysis of variance, but again, we're only covering section 12.1, which is going to be the one-way ANOVA. So in order to construct this, or in order to work with this one-way ANOVA, what we're going to have to do is we're going to have to develop how we're going to be looking at these contingency tables. So let's start off with the definition for this one-way ANOVA, that way we can start moving into that material. So a one-way ANOVA is defined as a method of testing the equality of three or more population means. Alright, so here is where we're comparing, or we're testing that equality, see if the means of three or more populations are going to be equal or not, and we're going to do that by analyzing sample variances. Alright, so within each sample, we're going to now start looking at the variance for that sample. And we're going to do this analysis again just to make sure, or to see whether the population means for each individual sample are going to be different or drastically different from one another. So, what are the hypothesis tests going to look like? So the hypothesis test that we're going to be looking at, the null hypotheses, is always going to be the same for this ANOVA testing type of problem, where all of the population means are going to be equal to one another. The null hypothesis, the alternative hypotheses, this is a hypothesis that we're going to look so that we can try to reject the alternative, so that we can try to reject the null hypotheses, is that not all of the population means are going to be equal. So, what we're looking for here, again, we're going to be looking at each individual sample and calculating the sample means. For these, they're all going to be x bars. X bar sub 1, that means sample 1, we took the mean. X bar sub 2, that means we took the second sample's mean, so on and so forth. So, if all of the sample means are close together, then that means that the null hypothesis is still kind of holding, which means we're going to fail to reject the null hypotheses. And again, fail to reject means that we're not accepting it, but again, we're not rejecting it at this time. There's still some data that says, hey, this could possibly be true, we just don't have enough data to reject it. Alright, that's what we get here. Now, for the second part, if all of the sample means are far apart, and we can kind of put this far apart in quotations, right? How much is that far apart? Where is that cutoff score that we're looking at? But if they're all far apart, then far enough apart, then we're going to reject the null hypotheses. Alright, so how do we then go ahead and satisfy this far apart, right? It seems very ambiguous. But as with everything that we've been doing so far, once we got into chapter 7, when we were doing confidence intervals, chapter 8, hypothesis testing, chapter 9, chapter 10, 11, and now chapter 12, we always have to look at a level of significance. This level of significance then will allow us to then start observing how far apart do we want these to be. Right? If they're anything more than a certain amount, well then we're going to start rejecting the null hypotheses, and if they're not too far apart, well then that means they don't fall within that rejection region, which means we fail to reject the null hypotheses. There are a few requirements that must be met in order for us to be able to run these tests, or this ANOVA test, on a problem or on a sample. We must check that the population must have a normal distribution. Number 2, each population must have the same variance. So we're going to be looking for the population to have the same variance. Alright, we'll keep that in mind. And then samples are independent, and they must be simple random samples. If that is all met, then we're allowed to go through the ANOVA testing. Step 2, level of significance. We're going to be using alpha. And remember, alpha, oftentimes it is given to us saying, hey, I want you to test this hypothesis at this level of significance. If it is not given, once again, we always default to using 0.05. Step 1, hypotheses. This is what we were looking at right up here when we were talking, This is what we were looking at when we were looking at the beginning. Sorry about that. This is what we were looking at when we were looking at the hypothesis up here. All the population means are going to be equal, and the alternative hypothesis says that at least one of the population means is going to be different from the others. Now, what type of test is this always going to be? This is always going to be a right-tailed test. Very similar to when we were working on chapter 10, when we were working with correlation. With correlation, we were always using a right-tailed test, and then after that we went into chapter 11 when we were working with contingency tables, goodness of fit. And when we were working with the goodness of fit, that chi-square distribution was always a two-tailed test. However, this particular method for ANOVA testing is always going to be a right-tailed test. So it's important for us to keep that in mind. Always a right-tailed test. Next, what are we going to be looking for? What are we going to be looking to extract? One of the items that we want to extract, you're going to see here that we have 2 degrees of freedom. 1 degree of freedom, or 1 degree of freedom that we're going to be looking at for, is going to be for the factors. So when we say, hey, we're looking for the degrees of freedom for the factors, that's going to be k minus 1. If we're looking for the degree of freedom for the error, we're going to be looking at k times n minus 1. Now, these formulas are given here if we were going to do everything by hand. So, at this point in time, we are not going to do these calculations by hand. We're actually going to be using the TI-84 to give us a lot of these calculations. We are going to be doing some of these calculations manually. However, we're going to be allowing the TI-84 to give us a lot of those numerical values. So when I ask what is the mean square for the factor, what I'm looking for is this particular formula here. The mean square for the factor is just going to be this individual, or this particular formula. Awesome. Same thing for the error. If I'm looking for the mean square of the error, I'm going to be looking for this specific formula. Test statistic. Notice the test statistic that we're looking for here. The test statistic in this particular case is going to be f, and it's going to be the mean square of the factor divided by the mean square of the error. In other words, this is looking at the variance between samples divided by the variance within the samples. Now, I'm going to highlight this because this is one of these important formulas that kind of gets overlooked a little bit. And the reason I say it kind of gets overlooked is because sometimes we get too focused with, no, we just need the mean square error or anything like that, and we accidentally bypass this whole interpretation that it's just the division, or it's just the ratio between the variance of the variance between samples and the variance within samples. Now, if we want to use the p-value method, using the p-value method, what we're going to be doing is we're going to be analyzing it with this specific let's say command on the TI-84. This is going to be capital F CDF, and we're going to be looking for a few items when we do that. Alright, we're going to be looking at an initial F value, we're going to be looking at an upper bound, the degrees of freedom for the factors, and the degrees of freedom for the error is what we need here. Alright, and then the same thing is going to apply. If the P is low, the null must go. After that, we're then going to be able to write a conclusion whether we're going to be rejecting or failing to reject the null hypotheses. So, to illustrate everything that we're going to be using, let's go through and let's start this example. That way we can see how we're going to be analyzing and how we're going to be using all of those formulas that we were just discussing. So, let's start off. We have 3 groups of randomly selected students. We're given a different dosage of, wow, that's a really long word, statistioprazole. Wow. Let's call this esprozole. I'm going to abbreviate this. There we go. Alright, so they were given a dosage of esprozole, a new drug that supposedly increases a student's ability to perform statistics. Wow, if they really sold that, I want some, because wow, that's awesome. Now, each group was given a statistics pretest. Then, 2 groups were given a certain level of esprozole for 2 weeks, while another group took a placebo. Then, all groups took a post-test out of 10 points. The data is assumed to be from populations that are normally distributed with equal variances. Alright, so here's where they're telling us, hey, these populations are normally distributed, so that's kind of important for us to do, or to analyze. Populations that are normally distributed, and they also have equal variances. If you notice right over here with these requirements, we were asked to make sure that each population has a normal distribution and each population has the same variance, and the samples are independent and simple random. Well, we just got 2 of them. The population is normally distributed and they all have equal variances. Alright, now they also told us at the very beginning that groups of randomly selected students, so we actually met all of the 3 requirements, which is really good. So the question now says, test the claim that the mean test scores are the same for each treatment with a significance level of 0.05. Alright, so we got some work to do here, or we got some job to do. Alright, so I'm going to state the null, and then after that I'll state the alternative hypotheses. So the null hypothesis is going to be that the population mean is going to be the same for all 3 groups. So what I'm going to do here, the placebo group, I'm going to say the mean for the placebo group is going to be equal to the mean of the 10 milligram group. Alright, that's a 10 right here. And it's going to be equal to the population mean of the 20 milligram group. So again, one group took a placebo pill for 2 weeks, another group took 10 milligrams for those 2 weeks, and then the other group took 20 milligrams for those 2 weeks. Alternative hypotheses. At least. So at least one of the mean test scores is different from the others. So we're looking for one test score to be different from the others. Okay, nice. So that's what we have here so far for this null and alternative hypotheses. Now what I want to do is I want to start filling in this table before I go through and before I run my test statistic. So let's go through and let's go ahead and start filling in this chart. Now on this chart down here, it says that I want to know what is my sample. Alright, how many values are within the sample? Well, n value for the placebo group, that's only 4 people. 1, 2, 3, 4. How many people in here for the 10 milligram? 4. How many people here for the 20 milligram? 4. Simply because they're only giving us 4 different outcomes. Now I need the average or the mean here. So I need to go through and I need to find the mean for these specific samples. Now you can do this by taking all of the values, adding them up, and then dividing by 4. That's completely fine. Or we can do them on the TI. I prefer to do them on the TI. So let's go to the TI. Alright, so here we are, TI 84. What I'm going to do is I'm going to insert these lists into the actual list. So I'm going to go here to stat. I'm going to edit the list. Alright, I'm going to go all the way up to list 1. I'm going to clear this, press enter. There we go. Now I'm going to start entering the values. So for my first list I had 6, then 8, then 5, then 3. Awesome. Go over to list 2. Let's clear list 2. Clear, enter. List 2, this is a 10 milligram group. 9, 6, 6, then 8. Group 3, this is a 20 milligram group. 8, 10, 9, and 9. There we are. I'm going to exit here. There we are. So now again I'm going to run a one variable statistic here. So I'm going to go back to stat. I'm going to go over here to calculate, and I want this one variable statistic. One variable statistic, I need to run this on 3 different lists. List 1, list 2, and list 3. So I'm going to do this one by one. Alright, so I'm going to do list 1. There we are. Alright, here we go. I have my X bar, my average, which is 5.5. And I'm going to have my standard deviation here. Notice, we don't need a standard deviation, we need a variance. So we need to find that standard deviation. But it's okay because that just means we have to square the standard deviation. Alright, so let's go back, let's write this down, and then we'll keep going from there. Alright, here we are. So, I'm going to be using, again, this is for the placebo group. So I'm going to write on here placebo. So the mean here is going to be 5.5. So the mean here is 5.5. Make that a little bit better. Here we are, 5.5. Standard deviation. How do we find the standard deviation? Well, sorry, I have variance. Well, the way we're going to find the variance is by taking this standard deviation, and we're going to need to square it. So this is my standard deviation, and I need to square it. So what I'm going to do is I'm just going to truncate this really quick. I'm going to truncate it down to about 2.08. So I'm only going to be looking at this individual piece here, 208. So let's go ahead and let's square that and find out what the square of that is. So I'm going to use my TI for that. Here we are, so 2.08 squared. There we go. And this is that variance that I'm looking for. Alright, nice. So I'm going to go ahead and write this over there. So let's go ahead, follow me along. Alright, so I was able to get my variance here. Alright, so again, that variance is that standard deviation squared, so that's 2.08 squared. And that 2.08 squared got us at 4.3264. Awesome. Now I'm going to need to do the same thing for the 10 milligram group and the 20 milligram group. So if you were following along, all I have to do is find the one variable statistic for the 10 milligram and the 20 milligram group. So go ahead, put pause on this video and do that for yourself on the TI-84 now. I will be doing it as well, and when I come back I'm going to have all of that filled in along with these little snippets from the TI-84. So again, please don't wait for me to do it, but instead do it on your own. Really, put pause. Alright, here we are. So I was able to then extract list 2. List 2, this is for the 10 milligram group, and here we're able to see the mean and the standard deviation. From the standard deviation, we need to get the variance, and that's where I did 1.5 squared to get us 2.25. Mean was 7.25, there we are. Third group here, third list. So for this one here, the mean was 9, there you go, mean was 9, and the standard deviation squared, in other words the variance, was 0.66667. I did some rounding off there for this specific standard deviation when we squared it. Now, what we're going to need at this point in time is we're going to need to find the variance between samples, and we're going to need to find the variance within the samples. I would rather do this second one first, the variance within samples. This variance within the samples, all this is taking the variance or taking the mean of all of the variances. So for this specific value here, this is going to be the mean of the variances. Awesome. So the mean of the variances, in order for us to be able to complete this, we need these variances to be in a list, that way we can calculate it. So let's go through and let's find that calculation first. Alright, so follow me along. Alright, here we are on TI. Now again, when you want to do the analysis for the variance within the samples or the variance between the samples, you need to find the mean of the variances, and we're also going to need to find the standard deviation or the variances for these variances that we're looking at. So let's go ahead and let's create a new list. So I'm going to go here to list, so stat, edit, and I'm not going to touch list 1, list 2, or list 3. Instead, I'm going to go over to list 4. I'm making this new list, list number 4, and list number 4 is going to be this list that contains all of the variances for the individual samples that we were observing. The first variance was 4.3264, enter. Second variance for sample 2 was 2.25. The third variance for the sample was 0.6667. One more. There we go. 67. Awesome. So this is my list. It only contains the 3 variances because, again, we only had 3 samples. I'm going to exit. Now I'm going to run a 1 variable statistic on that list. So calculate 1 variable statistic. I need it on list 4. Currently I have it on list 3. So what I'm going to do is I'm going to access list 4, which is right here above the number 4, but it's in blue. So I'm going to hit second, list 4, enter, enter, and enter. And here it is. These are the magic numbers that we need. So let's go back and let's write all this down. Alright, so this new list that we generated here, so this is the list that contains all of the sample variances. And I'm just going to say sample variances. There we go. So to find the mean here, the mean is just this 2.414. So that's the mean that we're looking for. So the variance within samples, in other words, the mean of the variances, that's what I'm looking at here. Which means this is going to be 2.414. Awesome. Now, variance between the samples. In order to do this, we have a formula here that says, hey, all we need to do is take this n. So the n here is going to be the number of samples, sorry, not the number of samples, the number of items in each sample that we're looking at, which is just 4 all across the board. So this is going to be 4 times the sample standard deviation, or the sample standard deviation for all of the means squared. That tells me that we then need to look at this standard deviation here, and we're going to need to square it. So I'm going to take this standard deviation here, and I'm going to square it. So this is going to be 1.835 squared. And that's what I'm going to put in here. 1.835 squared. There we are. So now all we need to do is we need to calculate these values. All right, or this first value here. So I'm just going to do this on my calculator. 4 times 1.835, and then I'm going to square that 1.835. And in here I get, let's actually change the color back to blue here, 13, whoops, that looks like a B. 13 point, let's say 469. There we are. So what I want to do at this point in time then is I now want to go ahead and I want to calculate the test statistic. So the test statistic, according to all of my work that I just did right up here, that test statistic now is going to be this numerator, which is this variance between the samples that I got as 13.469 divided by the variance within samples, which we got as 2.414. Awesome. So 13.469 divided by 2.414. I'm going to hit enter here, and I get 5.58. Awesome. So far I have this test statistic. Now what I'm going to do is I'm going to build upon that, and I'm going to find this p-value. So remember, the way that we find the p-value now is we're going to use FCDF. So that's what we want to use at this point in time. So let's go through and let's see what we're going to be doing here. We're going to have FCDF. There we are. And, excuse me, this is going to be the p-value. So I need my test statistic, which is going to be 5.58, my upper bound. Remember, this is always a right tail test. The right tail test, I'm just going to do some very large upper bound. There we go, 1E99. And then I need some standard deviations. I need to know what is k minus 1, and I need to know what is k times n minus 1. Alright, so there I need to go through and I need to identify what is k and what is n. So let's take a little bit of time and identify what those are. Alright, here we go. So n, what was n? Well, we're using n as just 4. What's k? K is the number of samples that we have. How many samples do we have? 3. So we have 1, 2, and 3 samples. N is the amount of samples within each group. Alright, so far so good. So at this point in time, I need my k minus 1. So k minus 1 is going to be 2. So this is just going to be 2 here. And again, this was at k minus 1. And the next one is going to be k times n minus 1. Yep, k times n minus 1. So k times n minus 1. So we can do that on this side here. K times n minus 1. K being 3, n being 4. So this is going to be 3 times 3, which is 9. There we are. And that was at k times n minus 1. Awesome. Let's go to the TI and insert this in. Alright, so here we are on the TI. So I'm going to go over and calculate that p-value. So I need that distribution, so second distribution. And if you scroll down, it should be the 10th one here, or as they denoted, just 0. So that's FCDF. We need a lower bound, which we found to be 5.58. We need the upper bound, which we said it's just going to be 1E99. Alright, some very large upper bound. Then we're going to need this k minus 1, so the degrees of freedom for that numerator, that's going to be 2. Degrees of freedom for the denominator, that's 9. Press enter, and lo and behold, we get a p-value. Let's go ahead and let's write this p-value down on our page. So that p-value was 0.0265. And again, we're going to be comparing this p-value to our alpha level. The alpha level, were we given one? I believe so. We were given alpha level was 0.05. So alpha level being 0.05. Now we get to cross-check these. All right, let's go ahead and let's cross-check which one is smaller, which one is larger. And this one appears to be larger by far, which means at this point in time the p is low. So what do we say? If the p is low, the null must go. So we get that we need to reject the null hypotheses. All right, what does that mean for us? All right, well, the conclusion. There is enough some apple. There is enough sample evidence to warrant cheese and crackers. There we go. To warrant rejection of the claim that the mean test scores are the same for each treatment. So there is enough sample evidence, so we are able to come to the conclusion that given this sample evidence, we cannot accept the null hypotheses, meaning that there is enough sample evidence here to support our alternative hypotheses. All right, but then again, we were testing the claim that the mean scores are the same. So when I write this, I'm not writing the conclusion to say that we support the alternative hypotheses, because the question being asked said, are the mean scores the same for each treatment? We know that we're supporting the alternative, but at this point in time, to write the conclusion more effectively, all we need to say is that the means are not the same, because that is what we were initially testing against. All right, awesome. So I want you to look at this part down here, the instructions. We're going to use these instructions on the next example. I'm going to write these in, or I'm going to highlight these in, let's say, green, because I'm going to be using these. We need this for the next example. All right, this is what we're going to be using. So let's go to the next example. And again, keep this highlighted portion, the one that we just highlighted, in your back pocket, because we are going to be using that for this next example. So a consumer agency randomly selected auto drivers who had similar driving records, cars, and insurance policies. The provided table gives the monthly insurance premiums in dollars by these drivers insured with one of the four insurance companies. So again, we have four insurance companies. We have State Farm, Geico, Farmers, and AAA. So at the 0.05 significance level, so they're giving me an alpha level, we need to test a claim that the mean monthly insurance premiums are equal, assuming their populations are normally distributed with equal variances. So populations are normally distributed. Awesome. That's one condition that we were looking for. Population variances are all equal. That's the second condition we were looking for. Finally, we're looking for randomly selected. And this is randomly selected, in this case, auto drivers. So the first three conditions are in fact met, and that's these three conditions. We were given an alpha level. Awesome. So now what I want to do is I want to start then analyzing this specific table set. And before I get into that, I can state my null and my alternative before I do that. So my null hypotheses, this is going to say that the mean for State Farm, so the mean for State Farm is going to be equal for the population mean for Geico, is going to be equal to the population mean for Farmers, which is going to be equal to the population mean for AAA. And I'm just going to say A cubed. Alright, AAA, I like this as just A cubed. Now, the alternative then, the alternative is going to say that at least one of the mean monthly premiums is different. Alright, awesome. Now, what I'm going to do now is I'm going to start inserting all of these into a list. So State Farm is going to go into list 1 for my list. List 2 is going to contain everything, all of these numbers for Geico. List 3 is going to contain all the insurance premiums for Farmers. And list 4 is going to contain all of the insurance premiums, monthly insurance premiums for AAA. So I want you to then take some time and start inputting these numbers into your lists. Alright, so take some time, go ahead and do that, and I will do it on my end as well. Alright, so here we are. List 1, list 2, list 3, list 4. I got all the values in there. Again, the first one is for State Farm, the second one is for Geico, the third one is for Farmers, and the third one is for AAA. So, now that I have all of this here, what I need to do is I need to find the mean for all of the values. Alright, just so that I can start looking at them. Alright, so I'll be looking at the mean for all of these samples in just a little bit. Alright, now what I do want to do, however, I do want to run this ANOVA test. So in order to run the ANOVA test, I'm going to go ahead and quit out of here. I'm going to clear all this. Oops, excuse me there. Let me charge my computer really quick. There we are, crisis averted. There we go. Okay, so what I'm going to do now is I'm going to go here to stats, and I'm going to scroll over to tests here, and I'm going to go down all the way till I see ANOVA. So again, you can go down, but going down it takes too long, so I'm going to go up. Instead, it starts me from the bottom of the list. Notice, hey, there's list, or there's the ANOVA that I need. It's on category H. Press enter, and then it says, hey, you want to now do the ANOVA test. What do you want to do the ANOVA test on? So, in order to enter this, we then have to identify how many lists do we have. Well, we have 4 lists. We have list 1, so I'm going to access list 1 by pressing second L1, comma to separate the list. I'm going to access list 2, comma to separate it, list 3, comma to separate, and then list 4. There we are. And then I close a parenthesis here. So this command here is going to run an ANOVA test with list 1, list 2, list 3, and list 4 all incorporated in there. Press enter. Check that out. It gives us every single thing that we need. Alright, which is really, really, really awesome. Alright, so now that we have this, we can now go through and we can now start moving into analyzing what it is that we need. Alright, so what I want you to do here is I want you to look at your p-value. Alright, it gives us the p-value automatically. Alright, so what I'm going to do really quick before we go on is I'm going to screenshot this, and then I'm going to go ahead and write this over on the notes for the class. Alright, so follow me along to that. Alright, so as you're going to notice, we want to find a test statistic, but typically the test statistic helps us for the p-value. Now, to find that test statistic, we actually already have it. That test statistic is given to us right in here. That's your test statistic. So for us, the test statistic here is just 2.167. Awesome. Now, how do we find the p-value? Well, the p-value is actually given to us as well. That p-value is the second part here. This is the p-value. So the p-value here is 0.1142. And again, to do the p-value test, we compare it to our alpha level, significance level here of 0.05, and then which one is lower? Well, which one's smaller? Well, the alpha level here is smaller, which means the p is not low, so the null must not go. At this point in time, we're just going to say, hey, we are going to fail to reject the null hypotheses. Nice. So what's the conclusion then? Well, the conclusion is that there is not sufficient sample evidence to warrant rejection of the claim that the mean monthly premiums are equal. Alright, so once again, I want you to then analyze what's going on here. Analyze and then start extracting. At the end of the day, did I really need a formula for this? Right? The calculator was able to do everything for us. However, if I do ask work to find this test statistic, we could have shown using work that in order to find the test statistic, we need a formula, and that formula is given here by taking the mean squares of the factor divided by the mean squares of the error. Now, mean squares of the factor, look at the mean squares of the factor. That's right here. That's 156.4583 divided by the mean square of the error. The mean square of the error is here, which is 72.1964. So if you do this division on your own, you're going to find that you actually get this value. So I know a lot of questions are in people's minds that why do we then need to go through this first example then in order to achieve this second example if we're using the calculator for the second example? Well, what I want you to do is I want you to analyze the numerical values that you're obtaining. So this test statistic, 2.167, where it is that we get it. Why is it that we get this? Certain type of softwares don't give you the test statistics. Certain types of software only give you the mean square of the error or the mean square of the factor, and you then have to do the manual computation yourself. Alright, again, for the p-values, not all the softwares give you p-values, which means if you don't know the p-value but you do know everything else, then we can still find that p-value. So the underlying question, what is going to be on the exam and how is it going to be portrayed? The exam question can come in an example like this, or it can come in an example like this where I want you to then fill in the table yourself. If you fill in the table yourself, then that means you're going to have to go through these calculations here or through these lists in order to evaluate what is the mean and what is the standard deviation. Alright, so there are different types of questions that I can ask, and you will see both of these on the final exam. So it's going to behoove you to study both of these examples. Alright, so I hope you all enjoyed the lesson, and that's actually it for statistics. So I congratulate you all for making it through. And if you have any questions, again, please feel free to email me. Alright, I hope you all stay safe and make safe decisions.